Now, every month we put together topics for this webinar, Modern Hydronics and Heat Pumps. And of course, there's many different types of heat pumps out there on the market, and one of the very common ones are ductless mini splits, and they do have applications, but I do want to do a comparison between air water heat pumps and ductless mini splits. And as Kevin and I were talking, I want it to be a supported comparison. It's not just an opinion. It's looking at what different systems can do realistically and what they can't do. So what we're going to take a look at in today's topics, what air to water heat pumps can provide that ductless mini split systems cannot supply. We're going to take a look at one way to configure the Enertech AV, that's the air to water heat pump system, along with heat recovery ventilation, which is part of providing an overall HVAC application. And I'm going to give you some cost comparisons. And obviously, anytime we do cost comparisons, the cost can vary by market. They can vary based on just local material costs, contractor overhead, and so forth. But I did do some due diligence in trying to put these cost comparisons together. And the bottom line is you'll see these systems are comparable in terms of what the overall cost is going to be. And I always like to start off with when we're talking about HVAC systems, and in particular, we talk about hydronics. One of the selling points for hydronic systems for decades, when it is done correctly, it delivers unsurpassed comfort. And comfort is different than just supplying BTUs into a space. So I have this concept, I call it BTUs in a box. So if you look at this little simple graphic here, a building is basically a box, or even a room within a building could be considered a box. And those arrows pointing out are the losses, the heat losses through the ceiling, through the walls, through the floor, windows, doors, and so forth. And we have methods to estimate that loss depending on how cold it is outside and what we want as an indoor temperature. And from a thermodynamic standpoint, if we can replace the BTUs that are being lost at the same rate, it doesn't really matter what system is doing that. From a pure thermodynamics concept, when the heat supply rate is equal to the heat loss rate, the thermodynamics are satisfied, and what you should have is a stable indoor temperature under that condition. Now, again, we don't want to confuse comfort with just a stable indoor temperature, a stable dry bulb temperature. There's many other things that affect that comfort. It can be the temperature of surfaces in a room. It can be the airflow velocity. It can be the humidity. Even from a physiological standpoint, noise is part of comfort. We want low noises. So I have this concept I call BTUs delivered, except during defrost. And you see the photos there show some ductless mini split systems. And again, they can be sized so that they're capable of delivering BTUs into the space equal to the rate of heat loss. And the BTUs come in the form of a forced airstream coming out the bottom of one of these wall cassettes. Is that all you need for comfort? And my argument would be no, it's not. And just to be a little sarcastic, I guess, over on the left, there's something you can buy from Amazon. They're called hoodie footies. And I have actually talked to people that do wear things like this in their living room to watch TV at night, and they just assume that's what's necessary. And I feel that is a big compromise. So with properly designed hydronic delivery systems that look at both air temperature as well as surface temperatures. It could be radiant panel heating from the floor, the wall, the ceiling. It could be these panel radiators. But in the bottom line is we can better supply human physiological comfort using hydronic-based systems compared to all air systems. Okay. Now, I want to give you some context. How did we kind of develop this topic? A couple of years ago, I went to a conference to present It was the Building Performance Association. And there were 250, 300 people there. And many of them were interested in heat pumps. Not all of them would really have much interest in hydronics, but heat pumps was definitely a buzzword. I presented a session on air to water heat pump systems, and there was a lot of interest, and we had quite a few follow-up questions. But what kind of stuck in my mind is that we had a fellow come up who worked for one of the state energy offices, and he told me we've had several inquiries about air to water heat pumps, and we've tried to reach out to some contractors. And what we found is that it's difficult to find at that time, this was 2 years ago, it was difficult to find installers that were familiar with the equipment or willing to install the equipment. And I think part of that resulted in cost estimates or quotations that were significantly higher compared to other options, such as ductless mini splits or a central heat pump system. And that kind of stuck in my mind. And I said, is that really true? Is that that ductless systems are necessarily the lower cost systems? So I wanted to make what I call apples to apples comparison for a ductless system that can also supply with additional equipment. It could supply domestic hot water as well as heat recovery ventilation. So we look at these four functions here: space heating, cooling, domestic water heating, and heat recovery ventilation. This is really a complete HVAC package for a modern new construction house, especially houses that are being built for net zero or houses that are being built to passive home standards. Very tight, very minimal amounts of uncontrolled air leakage through the building envelope. And I based it on a nominal 4-ton heat pump system and 5 heating zones. And so that's the context that we're going to develop these two different approaches based on that. So let's start with the mini split approach. So if we look over here on the left, here's our outdoor condenser. And if you've never seen one, here's an example of an outdoor condenser. And you can see all these line sets. These are refrigerant tubes, supply and return, and that white material is insulation. And there's actually 10 of these tubes. So I'm showing for each one of the 5 indoor wall cassettes, you've got a liquid line and a vapor line. And this is all copper tubing. It all has to be insulated, not only to minimize heat loss, but to prevent condensation when it's operating in cooling mode. You have to have wiring from each one of these indoor cassettes that goes back to, I call it the mothership outside, the outdoor condenser unit. So there has to be communication there, as well as power to run that indoor fan. You also have to have a condensate drain from each one of these indoor units. And it might go out through the exterior wall and just drip outside on the ground, or it might have to be routed to the building's DWV system, the waste system with a suitable trap, and where codes would allow that. So there's a fair amount of what I call infrastructure that's necessary to connect one of these indoor units to refrigerant tubes, condensate drain provision, as well as electrical. Now, that portion of the system here, the ductless portion of the system, can supply space heating and cooling, but we have to add a separate system for heat recovery ventilation. So again, a heat recovery ventilator or an energy recovery ventilator basically is a heat exchanger between two airstreams. An outgoing airstream, let's say in the winter, it's going to be on a relative basis, it's warmer air, it's interior air that goes through the core of the heat exchanger. And then you have colder outside air coming in, absorbing some of that heat from the outgoing stream. And that becomes the preheated fresh air stream that then has to be distributed through the building through some kind of a ducting system. And there are different approaches. It might be a trunk and branch system. It might be what I'll call a home run duct system, where 2-inch flexible tubing is being used from some type of a manifold or plenum on top of the air handler. But it's a separate ducting system just to supply fresh air throughout the building. And then finally, We find a lot of people are interested if they're going with ductless systems. Uh, how do they do domestic water heating? Well, it's common to pick a heat pump water heater, and this is just representation of that. So that's a separate item. The heat recovery ventilator is separate, and then of course the ductless mini split. And just some photos over here. Here's a typical wall cassette. This plastic channel here just covers up the line sets inside. Here's a heat pump water heater. You can see the condensate goes down to a condensate pump here. Here's an example of a heat recovery ventilator unit from Zender. There's several brands out there. And this is an example of a common retrofit of a ductless system where the condenser unit, in this case, is mounted on brackets on the side of the house. And you'll see these plastic channels that route the refrigeration tubing up to wall penetrations that go through to the indoor units. And again, this is just 2 units. If you can imagine, maybe there's another unit over here and so forth. We've seen buildings with upwards of 150 feet of this exterior ducting enclosure system, all fastened to the outside of the building. So just a review, again, 5 separate copper line sets, 10 tubes in total required to pipe between the outdoor unit and these wall cassettes. Remember, it's a 5-zone system we're looking at. All those line sets have to have insulation on them, so it's not just bare copper tubing. And we have to have 5 line voltage wiring runs, each with 4 insulated conductors between each of the indoor wall cassettes and that outdoor condenser unit. So that is a solution. That is a workable solution. But is it an optimal solution, or is it competitive with other solutions? So again, final point, each of the wall units has to have that condensate drainage system provided for it as well. Okay. Now, one of the things that sometimes doesn't get discussed or thought about when somebody commits to a ductless system is maintenance. Each one of these wall cassettes has a filter, and I've cleaned the filters on these units. They're not hard to do. You basically pop the cover open and you slide the filter out. You take it outside, vacuum it. You can wash it with detergent and so forth. But one thing that isn't quite as easy is getting mildew off the inside of these units. And here's just a photo that shows that. Remember, when these units are operating in cooling, especially if you have high dew points, high humidity, you're going to get some moisture that will condense inside these units on the coil as well as on some of the plastic parts around the coil. And this will lead to mildew. So what we're looking at here in this upper right corner is a fellow, and he's got a small electrically powered pressure washer. And you'll see that clear bag that's been installed under the unit. So he's basically spraying a mixture of some type of a disinfecting detergent and water up into that unit. And he's catching that water as it drains out along with the, the remnants of that film that was in there. So the coil and the interior cabinets really need to be washed, and the recommendation is once per year. Really where you're going to get the most mildew accumulation is during the cooling season, but during the heating season, again, depending on the dust content of the space, you are going to get some dust accumulating. So you can see here's an example in the bottom center of a filter, a typical filter that comes out of one of these units. It's a flexible filter system, and it's caked up pretty good with dust. And if there has been some moisture in the air, or if there's smoke in the air and that type of thing, you're going to have a pretty dirty filter. Here it is when it's cleaned. Again, here's some side-by-side comparisons between dirty filters and clean filters. And over here is a cabinet. It just shows, obviously, this one has not had much maintenance to it, and it's pretty dirty. And I put a couple websites down here for you to check out. There's actually a website called WeCleanHeatPumps.com. It's a franchise that is developing now, and their sole purpose is to clean these units. Now, they do clean other equipment as well, but they were They were founded based on cleaning ductless split systems. And again, there's some YouTube videos that, if you're interested in what the procedure actually looks like, go to that YouTube, and this will all be coming out in the PDF that Kevin will send out after the webinar. But I encourage you to look at both of these websites and see what's involved with cleaning these units. Okay. Now, what's the hydronic alternative? And I'm giving you a pretty specific configuration over here. First of all, it's going to be based on the Enertech AV060. That's a nominal 4 to 5 ton air to water heat pump system. And that system includes the outdoor unit. Over here, you see the monoblock outdoor unit, the indoor unit, which houses the circulator, the valves, the controls, the expansion tank, the auxiliary heater, and so forth. And it also includes a TurboMax, what I refer to as a reverse indirect tank. This is a tank that is used for creating domestic hot water. So the Enertech AV system is truly a system in that it provides for heating, cooling, and domestic hot water. And the space conditioning outlet pipe here goes up to a 3-way diverter valve. This could be a valve that's operated by a 24-volt signal. Basically, it takes the upgoing flow here, and I'm showing it in a blue line. So let's say we're in cooling mode. And in cooling mode, it's going to divert that chilled fluid up through the coil of an air handler. And then the fluid, as it absorbs heat, comes back into the indoor unit. If we're in space heating mode, the valve flips to the other direction. And basically, I'm showing it going over to some type of a manifold that supplies panel radiators. Now, again, I'm just picking panel radiators in this example. These could be radiant circuits like radiant floor circuits, radiant walls, radiant ceilings. They could be convector units as well, but panel radiators are designed for space heating only. These are not designed for chilled water. They have no provision to collect condensate. And just to keep everything electrically controlled, we're showing thermostats here. So these thermostats would come back to valve actuators on the manifold. This hardware is it's available from dozens of suppliers today. It's readily available. Here's an example of a heat recovery ventilator. You can see there's 4 connections on it. Basically, 2 of those connections are the outgoing stream. 2 of those connections are the incoming stream. There's a couple axial fans that drive the airflow. And one of the things I wanted to show you, which I felt was a pretty unique product, and we've used this on some applications, and I've been very impressed with it. These grills that go on the bottom of interior doors. What this does is allows you to design the ducting system for the air handler. Basically, you're just designing and installing a supply air system. Because what these grills do is they are cut into the bottom of the door. You can see it's roughly 3.5 inches high. In this door, it's probably about 24 inches wide. And these grills are designed to allow air to flow through when the door is closed, but they also suppress light transmission and sound transmission. So the idea is you don't have to have a return ducting system. Even with the doors closed, the air can flow through these grills. And we're going to go back to a central location, and back on our schematic right here, I'm showing a filter grill. So this might be, for example, in a hallway somewheres in the building, a central location where return air that comes out of these different rooms can go to the central filter grill. And from there, hopefully it's a nice short run right back into the return side of the air handler. And you can see in this case, the heat recovery ventilator is also tied into the air handler. So our supply air ducting is dual purpose. It's there to supply cooled, dehumidified air when we're operating in cooling mode, and year round, it will supply fresh air. So we're getting double usage out of the supply side there. So again, a quick review: 5 panel radiators with 5 thermostats. So we do have a 5-zone heating system. We do have a single air handler with ducting for chill water cooling, We're using that return air grill to reduce the requirement on return air ducting. And we have tied the heat recovery ventilator right into the return side of that air handler. So that's the system that would be the alternative to the ductless. Okay. So let's again, I'm going to go through here and kind of compare ductless. That would be the red text versus air to water approach. With a ductless system with 5 zones, you have a lot more piping and electrical penetrations through the exterior walls compared to what you would need for the air to water heat pump. Essentially, the air to water heat pump, you have 2 pipes that go outside to the monoblock unit, 1.25 inch pipe sizes. You do have an electrical cable that goes through there. That's pretty simple to route that out there. So that compared to 10 different tubes that we have to bring in for the ductless system, plus each of those cassette heads has its own wiring harness. All the refrigerant tubing in a mini split or a ductless system has to be insulated. Now, in most hydronic systems, the piping conveying chilled water does require insulation to prevent condensation, but that is much less footage of piping compared to all the vapor and liquid line piping that is required when you have the ductless approach. Okay. And just a couple photos here. Exposed refrigeration tubing and electrical conduits adjacent to the condenser. They're subject to stress from heavy snow. Now, that upper right photo, I took that photo because I had to shovel that unit out. It was actually on a church, and combination of a very snowy winter plus people that were shoveling the roof and just allowing that snow to build up. That unit was completely buried in easily under 3 feet of snow. It wasn't operating under that condition, but imagine the weight that would be on this tubing down here. And you can, if you look carefully here, you can see just the weight that was on it has pulled that refrigerant tubing out of that plastic enclosure. It actually broke open the plastic enclosure. Here's kind of a zoomed in view. Somebody had repaired that with zip ties. But this piping out here is subject to not only damage from weight on snow, but potential vandalism. Depending on what the price of scrap copper is, it doesn't take long to cut some of that tubing and just literally rip it out and scrap it. So that is a vulnerability on those systems. Okay. Again, when we run tubing on the exterior of the house, we have increased material labor costs, compromised aesthetics. Some people don't care what it looks like. They just want the cooling or the heating. But for example, in this photo here, that is being run along wood siding. That's cedar tongue and groove siding. And I always have to ask, what's going to be the effect 10 years, 15 years down the road? Is rain getting behind that siding? Are bugs growing behind that siding? Is there going to be any deterioration or just changes in the pigmentation, for example, if it was vinyl siding protected from the sun? At some point, the ductless system is going to have to be removed at the end of its life. What is left as far as any effect on the siding? Okay. Now, besides the aesthetics and the potential impact on the siding, there's the aesthetics. There's increased heat loss. So all this piping, you can see here, the insulation has actually shrunk back away from that copper tubing. That definitely is heat loss. And one of the things, again, I've seen in my experience is within about 5 years, there's some pretty serious deterioration of that exterior insulation if it doesn't have some type of UV protection. There are insulation products that do have UV protection, and you can also buy tapes that you could wrap the insulation with that would absorb the UV. But some of this insulation gets very rigid and it literally starts to just flake away or crack open or otherwise deteriorate based on primarily sunlight. And of course, if you're starting to lose the insulation, you're experiencing increased heat loss. So I ran some quick numbers. If we had a half-inch copper tube, a vapor line, if it had half-inch foam insulation on it, if it were carrying 150-degree refrigerant and it was 20 degrees outside, it loses about 16 BTUs per hour per foot. Okay. The 3/8 liquid line, same insulation, operating at 110 degrees, would lose about 9 BTUs per hour per foot. So if we had a 5-zone system, and let's say collectively all 5 zones required 100 feet. Again, I'm picking a number. It's not, obviously not a guaranteed length. But if there was 100 feet of both of those tubes, we'd be losing about 2,500 BTUs per hour in heating mode under those assumed conditions, just by having that tubing outside. And obviously that is true loss to the outside. The hydronic system, typically you're going to have tubes like this that are routed within the building envelope, almost always within the building envelope. There are situations where piping might be routed in an unconditioned space, a basement or a crawl space. Most codes require insulation on tubing under those conditions. But the more common scenario is tubing, and we're looking at, this is actually half-inch PEX Alumina-PEX tubing that goes out to panel radiators. And you can see it's just being routed through the floor framing, all within the thermal envelope of the building. So heat that is lost from that tubing actually contributes towards the building's heating load. Okay. Again, same photos here, just the idea that a ductless system, to properly maintain it, it does require the filter cleaning as well as a periodic cleaning to remove mildew. Okay. When we go with a hydronic system and a single chill water air handler, oftentimes the air handler is not in the living space. It's not above somebody's sofa, not above somebody's piano. It's in the basement, or it might be up in an attic, or it might be in other type of accessible space that is not within the living space. So the idea of cleaning the coil, checking the filter, maybe replacing the filter, cleaning out the condensate trap, and so forth, that's not taking place in somebody's living room. So that is an advantage. Again, I put WeCleanHeatPumps.com and encourage you to take a look at it, as well as this YouTube. Okay. So let's keep going. Most mini splits require completely separate systems for domestic hot water heating. The Enertech system down below, and over on the right, those are just the two schematics that represent the two approaches there. With the Enertech system, you're buying the tank, and the controls are already configured to operate the system to heat domestic hot water. One of the common configurations that I hear people talking about or asking questions about is, can we do a ductless mini split system and combine it with a heat pump water heater? And the answer is yes, you can, but it's important to understand the thermodynamics of the situation. Just imagine a building envelope, just a box that's insulated. And we have one heat pump that is an air-to-air heat pump, like a ductless mini split. So we're gathering low temperature heat from outside, and we're adding electricity to that, and we're delivering that as higher temperature heat inside the building. So that first heat pump puts the BTUs inside the thermal envelope. The heat pump water heater then takes some of those BTUs, combines it with more electricity, and puts it into the hot water heater. So in a sense, the heat pump water heater is in series, or is cascading with the heat pump that does the space heating. And there are ways, and we've worked through the mathematics on this, there are ways to come up with what I call the net COP of this situation, the net domestic water heating COP. And because the heat pump water heater, in effect, is, I use the word scarf, it's scarfing BTUs that were put into the thermal envelope by the air-to-air heat pump. The net COP on domestic water heating is always lower than what the actual COP of the heat pump water heater is rated at, because the manufacturer doesn't know. Heat pump water heaters are great when you have a space that has unintentional heat input from machines or from sunlight or something that is not essentially being paid for. But when you have a thermal envelope and you have an air-to-air heat pump that is delivering heat, that heat had to be paid for once to bring it into the thermal envelope. And again, it tends to lower the net COP. So I can give you an example of that, just some nice, simple round numbers. Let's say the air-to-air heat pump is operating with a COP of 4, which is very respectable. Let's say that the heat pump water heater is operating with a COP of 3. The net COP on water heating actually works out to be 2. When you work through the total electrical energy that was required to first bring free heat from outside air into the thermal envelope and then add more electricity to put that heat into the water heater. So again, that is a possible configuration, but the net COP on water heating definitely goes down from what the rating of the heat pump water heater is. Whereas with a heat pump, the AV system, all that energy that is going into that domestic water tank. Now, I'm going to go back and correct myself on that. Most of the energy going into that domestic water tank is coming from the heat pump. They there is the possibility that there are electric elements that would heat that. If it's extremely cold outside, there is auxiliary heating that would go into it. But under the same conditions that we talk about net COP up here with the air-to-air system, uh, essentially the heat pump is doing the domestic water heating. I know of one project where the AV system is consistently keeping that water heater at about 130 degrees temperature. So your your true COP on water heating with the hydronic approach is going to be higher typically than what you'd have with the combination of the ductless system and the heat pump water heater. Okay. Again, a separate dedicated ducting system is required if you're going to put an HRV or an ERV in combination with a mini split system. The fact that it is a ductless heat pump means there are no ducts to use to distribute fresh air throughout the building. So that does add to installation cost. And of course, right now we're in the midst of it just seems an ever-changing refrigerant regulation environment. We've moved away from 410A. We're using 454B or R32. Down the road, it's likely that R290 propane, it will be used as a refrigerant. And the regulations vary with the politics of the day. When you do a hydronic-based system, you don't have to worry about the chemistry of the fluid changing. Water is going to stay the same. So one of the virtues of a hydronic system is that when it's properly designed and maintained, that water-based system really doesn't care what's adding heat or adding cooling to the water. It's still going to be able to flow through the pipes, and it's not subject to the regulations compared to what we have with refrigerants. Okay. With the ductless systems, there's a lot more joints. And in theory, all those joints are perfectly tight. You don't lose one molecule of refrigerant. In practice, that isn't the case. Flare joints that aren't completely tight with larger systems, if you get into brace joints tend to be pretty good, although there is a possibility that depending on how well the bracing was done, that joint could crack from stress. But just think about the number of joints and the potential for refrigerant leakage. And obviously, there's more poundage of refrigerant in a 5-zone ductless system than there would be in an equivalent, let's say, 5-ton monoblock heat pump. So I just spoke to somebody last week that was talking about one of the new refrigerants. It was R454B. They paid $150 per pound to have that refrigerant added. So refrigerant leaks can be very expensive. Not only 454B or R32, but even 410A leakage tends to be expensive, especially as 410A availability fades out. Here's an interesting one, and I actually had a son-in-law that had a ductless system, and I'm relating his experience. He had I believe it was a 3-head system, and what happened was, within a few months of installation, one of the condensate drainage pans in one of the indoor units developed a crack. So some of the condensate was dripping through this crack and dripping down and dripping on the floor. And so he called the installing contractor. The unit was under warranty. Parts were under warranty. But when the contractor came out to deal with it, they found out we can't just replace this drip pan. We have to replace the entire head. There was no way in this particular unit to remove just the drip pan and replace it with just, an uncracked drip pan. So they had to reclaim the refrigerant, disconnect the refrigerant lines, disconnect the condensate drain, disconnect the electrical, take the unit off the wall, put the new unit on, and then basically go through pressure testing, evacuating the refrigerant, the new refrigerant tubing, and putting refrigerant back in. Again, the refrigerant, the parts were covered, but there was a $600 charge for the labor, which was not covered under the warranty. So basically, I see these indoor units. They're a highly engineered product. They're very compact. Obviously, a lot of thought went into building something that is that compact. But in doing that, they also become somewhat of a throwaway. Unlike other larger HVA equipment where you can replace components, they seem to have a tendency that when there's a failure, perhaps there are some units that do have replaceable parts, but in this case, the entire head had to be replaced, and it's expensive, and it took the better part of a full day for that head to be replaced. Here's another one. From that same system. My daughter called me up one night. It was in February. She said, "Dad, how come the heat pump is blowing cool air?" And it was in heating mode. And what was going on? It was in defrost, and it was essentially scarfing heat from inside the building and using that heat to melt the frost on the outdoor unit. And that became noticeable. And again, different products, sometimes they shut off the indoor fan and so forth to try to minimize this effect. But the bottom line is when you defrost an outdoor coil, you have to have heat to do that. And typically with a ductless system, that heat comes from the interior of the building directly from the air. Now, in a hydronic system, that heat can come from other mass in the system. It might be a buffer tank if the system has a buffer tank. It could come from heat emitters. The AV system does have a provision to draw heat for defrost from either the domestic water tank or, if necessary, even use the electric elements. But the bottom line is the occupants of the space are not going to feel discomfort as a result of the defrost in a hydronic system. Again, imagine a system that has a radiant floor, a concrete slab, that has tremendous thermal mass, and the heat for defrost is easily attainable from that thermal mass without compromising comfort. Okay, so that kind of leads us up to, I'm sure, what you're thinking about. How much do each of these systems cost? I have contacted 2 different mechanical contractors. I asked them the same question. I want to do a 5-head, 4-ton ductless system. And I took both cost estimates and I averaged them out and came out to $30,500. That's an installed cost for the condenser, the 5 units, all the refrigerant piping, the wiring, ready to run. $30,500. I also got some quotations on HRV systems with dedicated ducting, $10,300 in round numbers to put that in. Installation labor for the HRV, the heat recovery ventilator system, including that ducting. The $10,300 up here, this is just material costs. This is what I estimated for the install labor. And then the installed cost for a 52-gallon heat pump water heater, $4,500. Again, I put down here, these costs obviously could vary depending on the supply chain, local labor rates, permitting, a lot of things can affect it. So you may say, well, that's high, that's low, but based on my area and based on getting some quotations on equipment, total cost in round numbers about $48,800, or round it off, $49,000 for that system. Okay. So here's what I came up with for the hydronic alternative. The material cost for the AV060 system, including the TurboMax tank, $19,000. Balance of system piping components. This would be the piping going out to the outdoor unit, piping going to the other portions of the distribution system, not including the panel radiators. Again, just material costs, $2,000. 5 panel radiators, I figured $900 per radiator for that. Air handler and supply ducting, $6,500. HRV and transition ducting, we have to connect that HRV system into the air handler. Right there, $2,500 for that. Antifreeze, this is a monoblock system, and antifreeze is necessary to protect the system from freezing. Wiring the system, and some miscellaneous I allowed, total $3,500, and then installing labor to put this together, $8,500. Came up with about $46,500. And again, these costs, you may say, my cost would be higher, my cost would be lower. What's the takeaway? The takeaway is both of these costs for the ductless system as well as this configuration are pretty close to each other, $46,500 versus roughly $49,000. On any given project, one might be slightly more than the other, but the idea that a ductless system is, for example, half the cost of a air-to-water system. And again, remember, we're doing systems that are complete here: space heating, cooling, domestic hot water, and heat recovery ventilation, a true HVAC system. We have very comparable costs. In my estimating, we're slightly lower based on the hydronic alternative. Okay. So again, I'm going to summarize, and then we'll go back to Kevin. We'll take some questions. So I'm looking at this from the context that modern homes, new construction, tight construction, for a true HVAC system, heating, cooling, domestic water heating, and heat recovery ventilation. There are some codes, I believe in Ontario, any new home construction, I believe, mandates heat recovery ventilation. I could see that coming in some model codes looking down the road, especially as building envelopes get progressively tighter, that eventually heat recovery ventilation may be a code requirement. So I've included it in our system design. Air-to-water heat pumps, such as the Enertech AV, combined with a heat recovery ventilator. And when you're using the same ducting for cooling and heat recovery or ventilation, cost competitive with equivalent ductless systems. And by equivalent ductless systems, the ductless heat pump combined with a separate system for ventilation, heat recovery ventilation, and a separate heat pump water heater for domestic hot water. Okay. The air water heat pumps offer advantages in terms of efficiency, maintenance. Again, with a single air handler, we're cleaning one coil in a non-occupied space location. We don't have the plastic gutters running along the side of the house, affecting the aesthetics of the house. Especially with panel radiators or radiant panels, we can provide superior comfort compared to an all-air system. So I feel that the hydronic system has some significant advantages, and that, again, we are very cost competitive with equivalent complete HVAC systems based on a ductless approach. So with that, Kevin, I'm going to go back. I know we had some questions submitted, and we probably got some more questions during the presentation. So let's take what time we've got and address them.
Yeah, we've got about 15 minutes here, and bear with me. We've got quite a few coming in here still. So I pulled a couple that have been submitted already. So let me start with those. Can your product, I'm assuming they mean the AV, be used to retrofit a boiler slash hydronic heating system in an existing house?
Absolutely. In fact, we have done a webinar on that in the past. So I recommend you go to the Enertech YouTube channel where there are archives of all the previous webinars. And we had one specifically talking about how to retrofit the AV system to an existing boiler. And quite honestly, I think that is going to be the dominant type of application as air to water heat pumps grow into the North American HVAC market. Because essentially the hydronic system, the delivery system is already in place. So yes, we definitely can retrofit to existing systems.
What's the maximum water temperature supplied for hydronic heating by this equipment? Again, I'm assuming AV.
Yeah. Well, that's going to depend on the refrigerant. The initial production of the AV units used R410A refrigerant. I'm going to give you what I feel is a reasonable upper limit is 130 degree Fahrenheit. Now, you might say, well, that means I can't use it with baseboard. That is not the case. Remember, even baseboard systems that may require 180-degree water under design load conditions, there's many, many hours in a typical heating season where the water temperature can be much lower and still maintain comfort in the building. The idea of outdoor reset control. And the AV unit, as well as the WV water to water unit, they both have the ability internal with their internal controls to do outdoor reset. So we can adopt heat pumps that are, in theory, would max out at 130 degrees. And we might provide, as an example, we've done some modeling on this in cold climates. We still may have the heat pump providing upwards of 90%, in some cases, even 95% of the seasonal space heating energy to a system that at design load might need 180-degree water temperatures. Now, the R410A production has stopped as of January of this year. Uh, Common refrigerants now, the AV system is using R454B refrigerant. There are other systems, air to water systems that are using R32. Typically, these refrigerants can get a little bit higher. And I'm going to give you, again, a nice round number, about 140 degrees. Now, I say that with a caveat. Um, as the outdoor temperature gets extremely cold, the maximum temperature may drop down. And if you look in the IO manuals supplied with these heat pumps, typically you'll see an operating envelope. And what it gives you is the maximum water temperature based on what the current outside conditions are. So if it's 10 degrees below 0 Fahrenheit, I don't think that these units would give you either 130 with an R410A system or 140 with the R454B. But again, that's well within what we can design hydronic systems for, especially new systems. And one of the points that I've tried to push for years in doing training is that any new hydronic system, my recommendation is at design load conditions, it requires no more than 120-degree Fahrenheit water temperature. And even lower is better. And now we're well within the higher COP performance region of these heat pumps. Now, remember, even a heat pump with, let's say, R454B operating 140, yes, we can make that water temperature. The question then should be, what's the COP? I would have to look it up. I don't know a number, but the higher we go in water temperature, the lower the COP is going to be. So it's still beneficial for a machine that, yes, could achieve 140-degree water temperature. It's still beneficial to operate that at lower temperatures whenever possible to keep the COPs higher.
They're still pouring in here. Someone wants to know where you bought those door grills at.
Oh, good. There's a company in New Hampshire called Tamarack Technologies. If you just Google that, I'm sure you'll find their website. I forgot actually what they do cost. They're not very expensive. I'm going to say maybe 35 or $40, something like that, perhaps less. And it's simply you take a saber saw, you cut a chunk out of the bottom of the door. They literally slide right in, just like a drawer. They slide right into that cutout, and there's a couple screws at the bottom that hold them in place. Tamarack Technologies in New Hampshire.
Thank you, John. Let's see. This was submitted a little earlier on. Does this analysis include refrigerant change cost, A2L to A3?
No, no, there's no assumption about going to a future by A3. I assume they're referring to a propane. There's no cost in there. Now, again, I can't. I'm only speculating that as you look at the A3 refrigerants and propane in particular, being highly flammable refrigerant. But what's the draw of it? Well, the global warming potential number for propane is 3. It's extremely low in global warming potential. I think 410A was 1700 or maybe even higher than that. I think 454B is probably in the 500 range, 600 range, something like that. Propane has, because it has a very, very low global warming potential, it's a very attractive refrigerant from an environmental standpoint. And quite honestly, that is what will drive its adoption. It's widely used in air-to-water heat pumps at this point in Europe as well as Asia. You'll find the main big players in those markets over there building air-to-water heat pumps they all have R290 heat pumps available. I don't know whether R290 will be approved for use in ductless mini split systems going forward. I don't know whether the piping would be sufficient. Obviously, being propane, the concern is flammability. And the heat pumps that are being produced now, as say in the European market that are using R290, they have unique design characteristics. For example, the electrical components are all isolated away from the refrigeration system as a precaution. They also have sensors in them that will detect any kind of a refrigerant leak, and they will shut down the heat pump based on that. They have an internal air separator. And the idea is if there ever was a leak of propane at a higher pressure than the water in the heat pump, the propane would go into the water stream. If there was an air separator inside the building, the potential exists that that propane would be vented by that air separator. And obviously, we don't want propane being vented inside a building. So when the manufacturer builds the heat pump around an R290 propane refrigerant, they put the air separator built into the outdoor unit. So again, as we go towards adoption of these low global warming potential refrigerants, questions would be, can an existing ductless system, and for that matter, can an existing system running on 454B be retrofit with R290? I don't know the answer to that. I suspect there will be cases where it may be possible, and I'm sure there'll be cases where it won't be possible. But the cost analysis I gave you did not include any type of future refrigerant change.
Got a lot of questions about the AV here. I'm going to throw 2 at you here. Barry asked, what type of refrigerant does the AV system use? And then I've heard it said that the AV system is designed for heating dominant applications. Can you speak to the available cooling capacity of the
Mhm.
AV system?
Yeah, as far as refrigerants, as of the January 1 of this year, none of the manufacturers could continue to produce 410A heat pumps. So the currently produced AV units are R454B refrigerant. And the AV unit has heating and cooling. It is not as if it just does heating and a little, it'll do a little bit of cooling. It does any air source heat pump, air to water heat pump is going to have higher capacity in heating mode compared to cooling mode because the heat generated by the compression is actually contributed towards the total heat the unit delivers. So it's outside air plus the electrical input, the heat from the outside air plus the electrical input to run the heat pump, that becomes the total heat to the building. In cooling mode, um, the cooling capacity would be the total heat dissipation of the heat pump minus that electrical input. That electrical input becomes, if you will, parasitic in cooling mode. So the cooling capacity of any heat pump is lower than its heating capacity. But I know of systems, many systems that are using the AV system doing whole house cooling and doing just fine. Just look at the ratings in the manual to, to make sure that the cooling capacity is adequate for the building you're using it in.
New ductless mini split units use A2L refrigerants, which are mildly flammable. This introduces design and installation considerations for these systems. In contrast, monoblock systems have fewer concerns since all the refrigerant is contained in the outdoor unit. What are your thoughts on this?
I totally agree. As we go to even with the A2Ls or especially A3s, uh, all that refrigerant is in the outdoor unit. In theory, you're much more likely to, if a leak were to develop, it's more likely that the leak would simply dissipate to outside air. So again, I don't know what will eventually be allowed as far as ductless systems, especially with A3 refrigerants, highly flammable refrigerants, if they will be limited to the A2Ls, the mildly flammable refrigerants. That's a question mark. And quite honestly, it's something that should be discussed and thought about. When we put a hydronic system in, one of the points I'd like to make is, and we made it today. Now, water isn't going to change. A hydronic distribution system, properly designed and properly maintained, is a long-term value proposition for the building. It will go for decades. And what puts the BTUs into that system could certainly vary, whether it's a heat pump, a boiler, cogen system, whatever it is, but water remains consistent. So we're building a distribution system around a known entity that is going to it's going to have the same properties today and tomorrow versus how will refrigerant changes and regulations potentially affect a, direct refrigerant system like a ductless system or larger systems, variable refrigerant flow systems where there can be hundreds, even thousands of feet of refrigerant tubing in the building. Will those directly transfer over to future refrigerants? It's a good question. I don't know the answer to that, but I do know with water, water's not going to change. So,
All right, we better call it quits there on the questions, guys. We will answer everything though, and send you a PDF in the coming days. John, let's go ahead and give us a sneak peek for next month.
yeah, next month we're bringing in a guest, Chad Marzatelli from Fernox, fluid quality and hydronic heat pump systems. Uh, Again, the fluid quality in any hydronic system is important, especially if we're mixing antifreeze in. We don't want to assume that whatever comes out of the tap in a given building is the proper chemistry for that hydronic system. So we'll be talking about additives. We'll be talking about cleaning, internal cleaning of hydronic systems to remove things like solder flux or just dirt that may be in the piping as the system is put together. We'll be talking about demineralized water, as a high quality base to which antifreeze can be added. So looking forward out, I'm being more or less narrating some questions and Chad from Fernox is going to be addressing those. So that's going to be a good topic for next month.
All right, that's going to do it for us today. Thank you for joining. Again, if you guys don't mind sitting tight for a minute and fill out that survey, we'd really appreciate it. In the coming days, like I said, you're going to get the Q&A PDF, the presentation slides, copy of the video, and a link to join next month's webinar. I hope this was beneficial to you and that you will join us again next month. Have a great rest of your day.
Thank you, everyone.
questions are still coming in. You're gonna have your work cut out for you, John.
Okay. That's
All
good.
right.
That's healthy.
Yeah. Have a good one, guys.